Thank you, Loops, and thank you for everyone for getting up this early, at night, basically, GPN time. So welcome to this talk. It's about 3D printing mainly. So in case you're here because you read the keyword patents and you think this is going to be a fun talk about patents, I'm sorry to disappoint you. It's not going to cover patents in too much depth, but it'll cover 3D printing and DIY projects and proprietary projects. Right, so let's start with part one. Where are we today? What's the state of the art for 3D printing? And how did we get here? Now, speaking of printing, of course, I refer to 3D printing, not the other you might have heard of. And it refers to printing, filament-based printing, so FDM printing or FFF printing, not the liquid-based, the resin-based, the SLA printing. There are many parallels, actually, looking at the history and the patents and all that, but that's not going to be covered today. So this is only about the FDM part. And if we were to agree on a company that brings most innovation in the recent years into the 3D printing community, I'm sure we would agree that this would be one company, and that's this one, Bambu Lab. Whether we like them or not, that's a different story, but the company bringing most innovation into that field definitely has been Bambu Lab for the last years. So if you look at their latest printer, that's the X2D, and this is actually a screenshot from their website. I have taken a number of the features that they're bragging with, that their latest printer has, and maybe it's worth keeping track of these and keeping them in mind. One of them is, well, multi-material has been there before, that's nothing new, but it has a dual nozzle, right? So it has several nozzles to print several materials. So keep that in mind, we'll get back to that later. It has not only a closed chamber, that's not new again, that's been there before, but it has a heated chamber. I don't think they're the first one with this one, but this is pretty new that the heating chamber is being heated. Also keep that in mind. It has, because of the heated chamber, an option to get in cold air from the outside, from room temperature, on room temperature, which is needed for fast printing because you want the printed plastic to cool very fast. So if you want fast printing, you need good cooling. So this is one of the features, and this is really new to what we know as printing. They do not use stepper motors for the extruder, but they use a DC motor. Keep that in mind as well, right? So this is, to my knowledge, the first printer that in the sphere of printing that we see that uses a servo extruder, a DC motor. Now again, to draw the lines, basically, speaking of printing, most of the printing that we see is based on one family tree, basically. So you can draw a very rough line as 10,000 euros, right? So everything that is below 10,000 euros, all that is being covered here is valid for that, speaking precisely and, unprecisely and compact. So this is the case for those. There are commercial printers that are above 10,000 euros. That's a different game. Right, so if you look at Bambu Labs, they appeared 2022. So the question is, what was there before Bambu Labs released their first printer? Who was basically carrying the torch of innovation in that field of printing? I'm sure you would agree on that as well. Any suggestions? I would say so too. Now that's the i3. That's, I don't know, does anyone of you, maybe it says it here, it says MK3 here. It's been iterated over and over and over again. That device has been there for quite a while. But before Bambu Lab printers appeared, this was the brand that brought most innovation. And if you have been in the field before, and if you think of that time, there have always been steps, new steps, improvements. But the one thing that really was annoying back then was the really slow speed, and there was nothing really happening there. And that's something that Bambu really changed. They made printing really still slow in a way, but they really accelerated by a lot. So printing became fast when Bambu Labs turned up. Right, so Prusa has been there before, and there are two more brands that need to be, or two more names that need to be, that we need to speak of. When we speak of what was there before Going back to the origin, basically, where does printing come from? Bambu Lab, Prusa. What is one more to mention? That's definitely Ultimaker. They were also in that field, and all derived from one common project that we're getting to in one moment, right? So, and the other brand would be Ultimaker. Sorry, that was Ultimaker. That would be MakerBot, right? So you see these machines that are the first generation machines. The new ones that you can buy today, they look somewhat different, but basically they're all the same, from the same family, and there's a lot of technology that they share that they still have in common. Now, if you go back in time and see what is the origin, what was there before that, where did it all come from, then you find that there's one project that a professor at university in Bath in the UK started, Andrew Boyer, and he said, well, wouldn't it be cool if there was an open source hardware project that allows you to print things? And the one thing you could print if you had such a printer would, of course, be parts for more printers. Of course, that's what you need, definitely. So he came up with this idea saying, okay, what if we have two classes of components? One class of components would be stuff that you can get in hardware stores, like threaded rods, screws, bolts, and also the electronics and the motors and all those standard things that you see here. And the things you see here in white and in green are the parts that you cannot get from a hardware store. And these will be printed. Right, so if you have one printer, you can create a second printer by printing those white and green parts and then buying the rest and then assemble that, and then you have a second printer. And from that you can print more printers and all that. So the question is, how do you make the first printer? Right, the second is easy. But how do you make the first printer? Because you don't have a printer yet. So it's a chicken and egg problem. And this is all being documented. There's the project this goes back to is the RepRap project for replicating rapid prototyping. You find that all in reprap.org, and it's very well documented. And there is one page showing the history of RepRaps and the development and the number of devices that were in existence over time. And if you look at the very first entry, you see that in 2007, the first RepRap Darwin, that was what the initial open source printer was called, was finished. Its RP, rapid prototyping parts, RepRap parts were made in a Stratasys dimension, right? So what does Stratasys dimension mean? Now, Stratasys is a company that produces printers, and Dimension is one of their products, one of their printers that was pretty popular at that time. So they used a commercial printer. There was no open source hardware printer at that time. That was what he started. They used a commercial printer to print those very first parts, so then they could print with that printer more parts for more open source printers. Now, if you dig deeper into their documentation, you'll find a manual that describes several aspects of how do you judge the quality of a print, how the supports work, and all that. And in one of those pages, you see picture 3 here. I have it a bit bigger here. And that is actually that device that he was referring to. And that is a Stratasys Dimension, right? Sorry for the low resolution, but that's the original picture. So this is the printer that started the printer that started all the rest of the printers that we see here, right? So this is the origin of the origin, if you wish, right? So this is a commercial printer. And of course, now maybe you can guess what's hiding below this cloth here. And the cyber stickers. This is exactly what we have here, right? So I'll remove that. And you see some similarity, right? So this basically, it's not exactly unchanged, but this basically is a Stratasys Dimension that has been the origin of the origin. Not that device, but that type of device, of course. We'll get back to that later and how we got into this. But first, let's look at evolution of printing and the roles patents play in all this. As I said, this was a commercial printer, so no open source. It was patented. And if you look at the initial patent that was granted for 3D printing, you see it's been assigned to Stratasys. We're not going to go into detail, sorry, don't worry. And it has been filed 1989. That's a while back. And it has been granted, that's my understanding at least, maybe someone of you is more familiar with reading those patents. It has been granted in 1992, that's also a while ago. Now, the cool thing I found, this is the first time I dug into a patent at all. The cool thing is, when you look at that, you need to describe in very much detail what your invention is about. How does that work? So there are diagrams. Again, we're speaking of 1989 when it has been filed, so it has been engineered, invented in the years before that. So it describes in very much detail how the machine actually works. You see on the right here the extrusion system. We'll not go into detail on that one. But if you look at this one, that's the mechanical setup for the printing mechanics. And you see, well, what do you see here? You have a build plate here. You have motors that are able to move this build plate in X and Y. So you have 2 dimensions. So you can, you have a third dimension, that's the Z. And you can move that nozzle here to every point in height. So with that X, Y, and Z system, you can put the nozzle in every place on that build platform, so covering the whole space, the whole volume, I'm sorry. So what happens is that you put the nozzle at some height, very low, and then you move the nozzle in X and Y, you print one layer, and then you move it up one layer, and then print the next layer and all that. If you've been doing 3D printing, I'm sure you're aware of that. The fun thing is that this whole system is still basically unchanged, refined of course, but the core system is still the exact same. You have an X, Y, Z moving system, you have a nozzle that heats the plastic that comes along with the filament, it melts it and then deposits it on a build platform. So the core system is still identical. Again, this has been filed 1989. And printers that you buy today, most of them would still be working on this principle. So the whole thing has been, well, invented, made up of thin air. There was nothing there to orient. There was this idea of making it and then inventing and building a machine that actually worked with all that, which would be able then to print something in 3D. 1989. But on top of all the mechanical system, how would that at all work? What is a filament at all? What do I need to do? What temperatures, what materials? How do I produce the filament? All that. Beside all the mechanical stuff, you also have the electronic stuff and the software. Now this is also described in this one diagram because it says, you see those 3 boxes there, the modular controller, that's the system that would control your motors to move the table, to move the nozzle, to heat the nozzle and all that. You have the layering software, that's something that you would call the slicer today, right? So that's the same thing again. And you have the CAD software that you need to model something at all. So you have the whole tool chain, CAD, slicer, and then controlling the mechanical system to actually do that print. So that has all been written down in the patent. Now, as annoying as patents might seem when you think, but it just allows me to use it commercially. There are some conditions under which you can use it. One of them is 20 years passing. One of them is non-commercial. But the good thing about it is it's a very precise documentation of how the whole thing works, which is the basis for, I could do this for myself. So this is what Andrew Boyer did in the 2000s years, like 2005, 6, and 7. And he said, let's start an open source hardware project that implements this again as open source hardware. So everything that is being produced and developed in this project will be released as open source hardware. So everyone can use it, build it, improve on it, release it, change it, modify it, everything you can do with open source software, but in hardware. Now, he was not the one to invent open source hardware, but he was using something that was very popular at that time already. That's something you might have seen before. That's an Arduino Uno. That was something that was invented in Italy. That's Massimo. I can't remember his surname. Does anyone have it here? Sorry? Banzo. Massimo Banzo could be an arts teacher. So he released this one, and basically what is it? It's a microcontroller that's just not just a chip. He didn't invent the chip, that was there. But he said if there was a board that would include that chip and make it accessible very easily. So you can you have those pins connected to those ports here, and you can then run wires from those pins to a motor, to an LED, to a heating system, whatever. You can control things and then write software using the Arduino IDE to do all that magic. So Andrew Boyer took this Arduino project. He basically had a second board, a shield that can be placed right on top of this, that would then run the controller, the stepper controllers and all that. So he was building on open source hardware because it was there and it was legal to use it, and then he would release the whole project as an open source hardware again. So from this, a big community was created because people were interested in this, and they wanted to improve on it, to use it, and to make sure that this is being usable, getting usable, and getting better. So from all this soup, basically, came all the projects that we've seen, and you've seen the names, Prusa, you've seen Ultimaker and MakerBot, and these are companies that were founded from this core soup, or the basis of all this. Now, if you look at I happen to know how Joseph Prusa, the founder of Prusa Research, started in all this. He got involved in the project, and what he did was, he said, well, it would be very handy if the build plate itself was heated, right? So he was the one who came up with this idea, and he took a PCB, an electronics board, and he made ran thick wires on it, basically. He produced that board, so when you run a high current through it, it would heat up. So he was the one who came up with the idea of a heated print bed that would be good for the prints because they would stick better. Now, today you would think that, yes, of course, heated bed, this is normal. No, it was not there until he had the idea. And he started his business with that. So he had this idea. He released his files and all his knowledge into open source, but still, he also, in parallel, he produced those boards. So he would sell these, and this is how his company started. Later on, he would print the whole, print, but also sell whole printers. But that was how he got started. So people were involved, helping the community and helping it grow. So basically what happened was there was someone having an idea, publishing it, the way we know it from Linux and from other open source software projects. And others would use this idea and say, that's brilliant, I'll do that. And some companies would use that again and produce printers and improve on that. So it was all a community that was working together, which meant this was all growing very fast. And everyone was able to contribute very easily. As you can, with an open source software project, you could just write documentation or have a small contribution or build your own better printer on the basis of what's existing. Now, this was the way it was. There was a situation back then. But what happened then, a while later, was that one of the companies, MakerBot was the first one of them, that was in 2012. They said, well, we thought about it, and we found out it's actually better for us if we stop publishing our results as open source, because it's something we made up, we invented, so we'd rather just only sell and not provide back to the community. So they were the first one to withdraw from all this, and they got a lot of backlash and shitstorms, and they were basically drawing out of this 2012. 2017 then, Ultimaker released filed their first patent. They did not have a patent by then, and this was the first one, which appeared very strange, and they said, this patent is only meant for defensive purposes. Right? So this means if you release something into open source, someone might come along and use this knowledge and file a patent. Now, if someone files a patent, he might, depending on the conditions, he might be able to stop you from using it. So you're the inventor, and someone else has the patent, and he can say, no, you need to stop this, you're not allowed to anymore. And just to prevent this, they filed patents in defense. Now, when you read this back in 2017, I was not in the field yet back then, but I can imagine that this sounds weird and you wouldn't believe them. They're just saying, but they'll probably attack someone. And to my knowledge, up until today, they did not. They did not. So they did file patents, but they never used it to claim someone. They just had this just in case they would need it. So they kept their promise. But also they started filing patents. And this is a news announcement that's from last year. That's by Prusa. That was from August. And Joseph Prusa, the founder, said that from his perspective, this whole open source 3D printing idea is dead. It's not going to work because there are too many players in the field that don't keep to the rules. They take what the community invents and makes up, use it in their products, sell their products, and improve on it, iterate on it, but do not release their improvements, which is not how it works. So this breaks the whole system. This helps that company, of course, but it's not playing to the rules. So he said, well, he's rather pessimistic whether this is going to work at all. That was in August. And in December, I don't know how those two messages are related. Sorry, I can't tell you that. This was a license Prusa came up with. That's the open community license. And it was trying to solve that exact problem. So allowing for the good use, whatever that means, and not allowing for the bad use, right? So but you need to write that in terms that really are solid and it can be, that you can go to, you know what I mean, when you go to court and have that sorted out. So basically what you can do with that license is you can download, you can use it, you can print the files, you can modify it, you can redistribute it and all that the way that you know it as a maker, and also as a company you can use that file, you can print your own printer, produce your own printer, and use that commercially to print things and sell the prints. You cannot use it to produce printers and sell the printers. Not with that license, you need a separate license. So this was their approach to say, okay, maybe this is a way we can distinguish between the good and the bad use. Is it going to work in the long time? We'll see in the long term, but that's their approach to it. You can, by the way, that's also a very interesting aspect. It's legal to use it to produce spare parts. So say you have this printer, it's 8, 10, 12, 15 years old. You want to repair it, and then you have the right to take those files and produce spare parts to repair your printer. That's a very good idea, I think. That's also perfectly legal. Right. So what is the key takeaway so far? Printing today has one common source. It's one open source project, and that has one source, and that's a commercial project, right? So this all goes back to this one. And there are several good arguments for using the patent logic, right? And there are good arguments for using the open source logic. So it can't really be said which one is the bad one and the good one. I think the one thing that is clear to understand is you need to play by the rules. So it doesn't work to say I claim, I take all the good from the open source community, but I won't give back. Okay, so let's get to part 3. How did we get our printer? And this all started with a phone call of a friend of mine. He called me and said, look, we have this printer. It's 15 years old. It's a proprietary printer, so it was not only expensive to buy, it was around 40,000 euros when we bought it 15 years ago. It's also expensive to run. So to run it, you need a specific filament that is being provided in cartridges, and you cannot use your own filament. You need to buy filament from the manufacturer. And the manufacturer sells the filament, the kilogram, for around 250 euros, right? So if you're in the 3D printing field, then you know this is something like 10 times of what you pay for a premium filament. So that really is very expensive. So the printer is old, it's proprietary, and on top of that, it's broken, right? So he said, this sounds like a perfect project for you guys. Well, he knows us. So we couldn't resist and said, yes, that sounds like that it was broken, which means that the print head was broken, and they had an estimate from the manufacturer to fix it, and that was around 5,000 euros. And he said, no, we'll not do that. For that money, we'll buy a new printer, and a proper one. Okay. So I spoke to him, can you just give me some dimensions, pun intended, some estimate on, how big is this printer, what is that? What kind of printer is that? He sent me this sketch. He said it's about 1 meter in length, 1 meter in height, and around 70 centimeters in width. So, okay, that's big. This looks heavy. How heavy is it? And he said, I don't know exactly, but I would guess around 70 kilograms, right? Keep that number in mind. We'll get back to that in a moment. So I asked Joseph here, what do you think? And he said, be real. We'll get this thing, and it'll be standing there in a corner. We'll be playing it for a while, and then it'll just collect dust. No one will spend any time, and it will just be standing there, wasting space. I said, yes, you have a point. This might actually happen. Mm-hmm. So let's make a deal. If we find that it's not moving anymore, no progress anymore, we'll have some second use. We'll dedicate it to, we'll build something else with it, like coffee machine, fridge, microwave, I don't know, something. I said, okay, deal, we'll do that. So we went there, we got the printer, and I mean, you see it here, but it nicely fills the boot of a Ford S-Max, which is not exactly a small car, but it worked. And this is the printer in front of the door of our makerspace. So it was all possible, but it was, it was not exactly handy. Now, here's one picture of the back of the printer, and you see that this printer is not an open source printer, right? There's some gem hidden here, so maybe you can see it. So you see all the list of patents that you see here. The top one, top left, that's the one that we've been looking into a minute ago. So it's heavily patented, right? So this is the Stratasys dimension. This is the printer it all started with and all that. Now, maybe you've seen it. Okay. So it was a very rough estimate, 70K, but I was really happy because had I known that this is the weight of the machine, I would have known we were never going to make it, right? So knowing that it's 70K, I said, okay, that's doable. So we went there, and got it. And then once it was in its place, we learned how heavy it actually is. Okay, so what we did was we opened the back and had a look inside, 15-year-old machine. So it was full of electronics, like all the controller boards and all that, and all the DRM stuff, of course. That is not necessary in current printers, in open source printers at least. And one of the things that you see here is a Linux machine. Here's the hard disk. This machine actually ran Red Hat Linux. Now I'm not sure whether anyone other than Harald is familiar with Red Hat Linux counting. Today you have Red Hat Enterprise Linux 10, right? And they're rather slow. It takes a few years for a new release to come up. So before Red Hat Enterprise Linux 10, there was 9 and all that. This is running a Red Hat 5. Now, not Red Hat Enterprise Linux 5, but Red Hat 5. That was before. So that's a really old machine. But it has a Linux machine. It has a VGA port and all that. Basically, what we did, we just threw that all out because we didn't want to use the proprietary technology anyway. So we left inside the power supplies here. They were pretty handy, that was clear, but we removed all the rest, including the CD here for recovery. So basically, we replaced it with these two boards. And, well, you can see it. This is kind of a Raspberry Pi, but on 24 volts. And this is a controller board, a 3D printer controller board that you can buy today off the shelf. Now, one remark, you can buy that. That's very easy to buy today. Why is it so easy to buy? Because of the heritage, right? This basically is nothing else than an Arduino board with that shield integrated into one, iterated and improved, including the stepper motors and all that. So it's not just by chance that this is so easy to get to work. It's because it's basically the same technology, right? It's just improved and minimized. So you have those two controller boards, those two boards that replace all the rest. So what we did then, we made a board to mount them on, and we mounted them in the back. You see the green board here, that's been removed in the meantime. So this is all that is still being left, that's controlling the machine. So the big question was, will that work at all? Because the machine itself is pretty big. It does not have a big build volume, although it looks so big. But it has a very, very robust and massive mechanical system. So it does not have the normal NEMA 17 stepper motors that you know from printers, but it has the bigger ones, the NEMA 23. And they're running a higher voltage, a higher current. So the question was, how do we get this to move? And we tried to find stepper controllers that would drive NEMA 23 steppers. And we had a hard time, and at some stage we just said, we just try. What should go wrong? If the stepper driver, Gesundheit, if the stepper driver was to break, we'll just replace it. They're not expensive. Okay, so we just hooked it up and see what happened. And here's the video of it. And the cool thing was, it just worked, right? So it just moved it. I mean, there's like 6 wires for the NEMA 23, whereas you only have 4 wires for the NEMA 17 normally, but that's easy enough. So pretty much we just hooked it up and it worked. Lucky for us. So, and there's another test that we did a few days later, and that was trying to get, okay, how fast is it going to be? And that looked kind of promising. We said, okay, this looks like it's not going to be a fridge, not a microwave. It's going to be a printer, I guess. So this is the picture that we made of the first print. You see the very valuable print bed here. It's tape that we used because we just wanted to make sure if something goes wrong that we don't break anything, because the original print bed is made of plastic. It's not heated, by the way. So it was really Joseph Prusa who was quicker than Stratasys. This is the first print that we made, and that looked kind of promising. This is the first cube. When it was finished, this it's far from perfect, right? Whoops, sorry. Far from perfect, but it was very promising. So iterating on that, we knew that we would get a printer to work. So I'm pretty good in time, that's good. So the one thing I would like to invite you is to visit us in one moment. What is the key takeaway for part 3 anyway? If you do get a weird offer for a weird project and you think, but it sounds cool, go for it. I can recommend that, definitely. It was a lot of fun. It was a lot of, we started work we picked up the machine in November 2024. And none of you are asking whether it's finished, because that's a weird question, I think. It's printing. It's printing very well. It has gotten a lot of attention, adjustment, and very precise adjustments. So you have the very good prints. Joseph took a lot of time to optimize that, so you can get your own print. I'm not sure whether he's printing already. We spent most of the day yesterday, by the way, trying to get the display to work with the controller board. And when we finally got on the Wi-Fi, we realized that it's not perfect, the Wi-Fi here. So we needed to have that cable running here, and this is not showing anything useful. Okay, but the printer is working. So if you want printouts, you can come and visit us at the booth that we have here, at the assembly, basically. So this is true for. Okay, this is the camera showing that. We'll get back to the camera in a moment. We have time, so I can show you some of the details also in the process. But if you ever get the chance to Offenburg, come and visit us, sit with us on our couch, our very special 3D printing TV that we have. So you find the calendar on our website, section 77, QR code up there. Join us on our couch. We're directly in the train station in Offenburg, so it's only half an hour with the high-speed train from here, so it's very good to reach. Yes, and if you ever get the chance to do a weird project, absolutely do that. So very quick on the look for it. You can, in the video, you can look at them in detail for the sources here, so that is all being sorted also. And now what I have is some of the technical details that we run into, because we have the time to go over them. If you have questions, just hit me with them, just ask. Otherwise, I'll just continue with these. Yeah, thank you. Sorry for confusing. Yes, you can switch back to the video, please. Thank you. So this is the printer currently running. You see that the print head looks special. And that's the story is that the original print head was broken anyway, so we removed that and replaced it with something that you would call standard print head today. But, you know, standard would mean that family tree and all that, you know. So it's pretty easy to do. So, thank you. So we'll switch back to the video. It starts printing and it'll print out around 10 minutes and then it'll finish. So here you can see the setup in detail. You have the print head. The extruder is behind that red plastic part, that cover. And you see the BL touch that is sensing the distance to the bed. Funny thing is, by the way, that the original printer also had, it was not a BL touch, but a sensor for the Z dimension. I have a picture of that in detail in a moment. Okay, so you see the whole setup here. This is actually the one big thing we changed in terms of optics. We wanted the machine to keep its original aesthetics, basically, and we wanted to change as little as possible. But this display had to go because it was, well, not impressive. It was, 15 years old, so it just had 4 buttons and those dot matrix displays. So we replaced it with a tablet, which runs Clipper, which is also a standard, family tree and all that. So it's normally, if you have a reliable network connection, possible to just control the printer from this. So you can start prints, you can see the progress and all that. So that's been replaced completely. And here you can see one of the things you can see here is the massive mechanics, right? So they're really stable rods that they have. And one of the things we would like to improve on and to as future work is getting the printer to print faster. And if you look at what does it take to print fast, you find several aspects. One of them is you need a stable mechanical system, right? So you can move fast. This system is stable, I would say. So yes, we have that checked. The second thing is that you need good ventilation. You need a lot of fresh air and strong ventilation. Now you see on this picture, you see that exhaust here, that small exhaust where the normally hot air would come out, because the original printer, that's one of the reasons it's so big, by the way. The original printer was made for printing ABS, and that's a material that is pretty hard to print because it needs a high temperature, and if you have a low temperature in the environment, then the printed part would warp, like it would contract, so it would solve itself from the actual print plate, from the print bed. So what they did to solve this problem was they did not heat the print bed, as we learned. This was invented later. But what they did was they heated the whole print chamber, right? So the machine was made for printing ABS only, and the normal operating temperature inside the print chamber was 80 degrees. That's one of the reasons the machine is so big. It has a lot of insulation to keep the warm inside, of course. So you see here, this is the exhaust for the hot air. And on the next picture, what you see here is you have 2 fans here. You have 2 fans on each side. So you have 2 fans on the left side, 2 fans on the right side. And they cover a heating element that is, you cannot see it here, it's on the other side of this metal plate. And this heats up the air, so there's strong ventilation, pushing air upwards, which is then being heated, and there are many hints that you find. If ever something goes wrong with the fans, make sure the heating elements turn off. You don't want the heating elements to run without the cooling, basically. So I'll go back one slide. So the normal setup would be that you have the fans down here, you have the heating elements, and the hot air is coming out here. So this is all being directed to the print bed. So as we do not want to print ABS and we do not want to have a heated chamber, we can use this to have proper ventilation. And this setup actually looks very similar to what you've seen in the first bamboo printers. They also have the ventilation there. I'm not sure you have that in mind on the X series. So I'm sure we'll have a very good ventilation on this one with the cold air. Okay, now here you see also the insulation on side and the mechanical system. That's very stable. And here you can see, it's not coming out very good in the picture, a mechanism for cleaning the tip, right? So this is something Josef has gotten to work also. So when you start to print, it would clean the tip, and then here's a poo container. So this is something you see in current printers as well. And here you have it's pretty much like a toothbrush, right? So the nozzle is being cleaned before it starts to print. Here you have a close-up of the BL Touch, of that bed sensor, bed leveling sensor, and that's the close-up of the initial BL Touch, or the bed leveling sensor. You see the plastic part here. It's hard to tell from the picture, but you see that one here, that metal part. So this is a mechanism that allows for activating and deactivating that BL Touch. If you're interested in that, you can come up to the assembly here, and we'll show you that. And here's also a close-up for the mechanism that is part of moving the filament from these cartridges and moving it back inside. My opinion is that this system is much more complex than the actual printing mechanism, right? So this is something that's pretty brilliant the way it's made, because it allows you just put in the printer cartridge and it would pull the filament through the whole system and then feed it to the printer. This is something we decided not to reactivate, but I found impressive to see how much effort has gone into that. Right, so that's part of the technical details of the features that were in the initial printer and some of the future work that we're going to cover. So I think we have something like maybe 1 or 2 minutes for questions if you have. Otherwise, you can come up to the assembly. You see us with our beach flag here. We're here. Yes, please.
How did they manage? Sorry.
There's a microphone.
How did they manage to protect their filament? How did the DRM work?
How did we manage to protect?
How did they manage to protect their filament? How did they make sure you couldn't use other filament?
Now I get it. Thank you. Now, when you buy such a cartridge, there's a chip in the cartridge, right? And it's the same thing as with, inkjet printers. So basically here you have a chip, right? And it'll know when it's empty. It doesn't matter whether you fill it, it'll know when it's empty. So just for optimum user experience, you don't want to print and have no filament left, although you think you see some. No. The machine will know when you have no filament left. Yeah. Does it answer your question?
Yes.
Okay.
So how much was this machine in the early days before the open source got in the 90s? How much did you have to pay? Could you please?
When you bought it when you bought such a machine in the 90s, I cannot tell you. That's a good question, but I'm sure it was not cheaper than when you bought this in the 2000s for 40,000 euros. So I cannot tell you.
You've mentioned that the stepper motors have 6 wires. What are the other 2 wires for? Is it like an encoder?
No, there are some ground wires, I think, but I'm not too sure. Maybe Harald knows by heart. No, sorry, I cannot tell you. If you approach me later, we can look it up. But that's something that can be neglected, so you can get along without. There are no encoders. That's for sure. It's a very simple mechanism. It's just coils inside the motor.
Do you think to re-enable the old cartridges to make it more original?
I would have loved to do that, yes. I would have loved to have a cartridge, just put a filament spool and put it in the cartridge, close the cartridge and put it in. That would have been excellent. I would have loved to do that. But I think the amount of work that would have gone into this is similar to the amount of work that has gone into the whole project. So I think it's very complex. Would it be a nice improvement? Yes, but I don't think we would complete that when we were to start. If people come along, like say, on a weekly basis, we're in our makerspace every Tuesday. So if people decide to say, okay, Tuesday night, I take the ICE train, I go to Offenburg and work on this project, we might actually do that. But otherwise, I'm not too sure. So feel invited to contact us, right? Okay, thank you.
Thank you so much for that wonderful talk. I personally have another very small question. What's up next for you personally with the 3D printing? Do you think you're going to continue improving on this 3D printer, or are you going to be looking for more 3D printers to improve yourself, or what's up next?
Who knows? We have more ideas for this printer, especially regarding speed. So as I said, the cooling system is something that would not be hard to get to work. So that would help increasing speed. That's the one thing. We also have an acceleration sensor. So if you look at current printer, they do calibration for resonance. So what you do then is you have an acceleration metering device. You put that on the print head, and you do some measuring. So you measure the resonances, and in the firmware, these measurements are then being used for calibration, so it can move more precise at the same speed or move faster at the same precision. So the sensor has been bought, and this is something that would definitely also help us improve speed and make it also faster. So we do have more ideas what to do with it. The question is, do we have enough time and dedication to improve on it? But we do have more ideas to make it faster. The mechanical system is so stable that it just, it just shouts, "Make me faster." So.
Okay. Thank you so much for this wonderful talk. Are there any very last questions? Oh yeah, another last question, please.
Are you still able to print with 80 degrees?
The 80 degrees, I'm not sure, that's a misunderstanding. The 80 degrees was the temperature that was inside the build chamber.
Yes,
so the nozzle temperature is around 200 and 220 degrees.
No, my question was, are you able to use temperature in the chamber of 80 degrees still? Because this is very nice for special materials.
Yeah, we would, but so far I tried to avoid it, because the thing is that the heating elements are the only ones running at 120 volts DC, right? So far we're only working with 5, 12, and 24 volts. You can't hurt yourself with those voltages. 120 volts, 20 volts, that's a different story. So I would like to avoid that, right? So, because new things happen then. So we were discussing using the heating, but not for 80 degrees. So you can, I think that's the compromise. You can say, okay, 24 volts, and then maybe have them in parallel and not in serial. So you get some temperature. 40, 45 degrees would be nice for most materials, and 80 degrees is something that you would need for special material only. So I wouldn't see too much motivation to go in that direction. It would be possible, yes, and if you have the right guardrails, then yes, you can do that. But I'm not too keen on going there. But if you come Tuesdays, maybe you're the one to do that.
All right, another wonderful round of applause for this wonderful talk. Thank you so much.
Thank you.